Hello and thank you for joining me. Today we're going to be revisiting an old topic, that being the in-body problem, how to solve it in Python, and then in this case you're going to be plotting it with Matplotlib. Last time I did a more of an animated two-dimensional thing. This one is still two-dimensional. It's a still image and it produces a plot of the path of objects, we'll say planets, stars, whatever, things in space subject to gravity. It shows how they behave over time according to a series of parameters with variable accuracy depending on a number of factors. As always, I have already completed operation of this program, or the development of this program. I find that this approach is much more convenient. Personally, I hate watching programming videos that take 3.5 hours because someone's programming it out while you're watching them. I wish to avoid that as much as possible, and as an added convenience, future me is going to be editing this down, hopefully into something coherent and educational. So I'm going to assume that you are already aware of the in-body problem if you're watching this video. I made a previous video on how it all works, the principle of determining how objects that are attracted or repelled from each other operate over time, and also how gravitation works under a Newtonian system. This is much harder to do using general relativity, and we won't really get into it because general relativity is fiendishly complicated, and I don't think I'm capable of explaining it properly at this point. But we can do the Newton thing. It's pretty useful for most of our contexts, and we're doing something two-dimensional anyway. Who cares? So we're going to be taking a look at the program for a minute while it is running in the background to show you what it does. First of all, we need to install some dependencies. In this case, random. We are going to be incorporating it as rand. We're going to be importing pyplot, of course, from Matplotlib with the abbreviation PLT, and we're going to be importing numpy as np. Out of all of these, numpy is by far the most important. It makes it super duper easy to do vector multiplication amongst other things. We can go over that in a future video, maybe. At this point we're going to get into the pyplot functions. Before you do anything with pyplot, you need to declare the existence of a figure. Sometimes you want to give it a subplot name like AX or anything like that. In this instance, we're only using a single figure. We're not getting too much information out of it. We're just tracking the paths of objects. So we're going to declare a plot.figure. You don't have to give it any arguments. You just have to tell it that it exists. You could do this at the beginning. You can do this at the end. It doesn't really matter. What we're also going to do now, for the sake of physical calculations, is declare some constants. I like to do this in a dictionary, but you can do it in any data structure of your choice. We've got big G for the gravitational constant. In real life, this figure is much smaller. In fact, in real life, this figure is 6.67. We'll make it a comment. Sorry, make it a comment. 6.67 e negative 11 meters cubed kilogram. I'll have to look up exactly how the units break out, but anyway, it's in meters, kilograms, and seconds. Because that's how this number is scaled, you need a separate value to declare the length of a second. That's very important if you want your dt value to change in your Euler approximation, because again, the smaller your change in time, the more accurate your values become arbitrarily. So you want to declare a dt delta time change in time. We've also got ET, which is epoch time or elapsed time, whichever you prefer, however much of a physicist you are. We're also going to declare a t-lim or time limit. That's the length of time we're going to let this simulation run. It's important that you establish a time limit or some sort of ending condition that won't take until the heat death of the universe, because your computer is fully motivated in that task, whether or not it is capable of accomplishing it. We're also going to, for brevity purposes, shave 3 zeros off all of our distances later and declare that a kilometer is equal to 1,000. That also means that each integer is a meter. Now we're going to declare some lists. We have an A list, active list, and we also have a D list, disabled. And we have a separate function to clear objects. Excuse me, I'll finish what I was saying. We're going to develop a separate function to clear objects from those lists, in this case based on the condition that object.active, a.active equals true. We'll save that in a temporary list, put it back in the active list. If it does not equal true, we put it in the disabled list. We'll see why this is important later on. Quick segue now that my example plot loaded. This is a pretty busy variation of what we're going to be getting out of this program. In this instance, we start with 25 objects. Their starting positions are the blue dots, and the ending position of the objects that are still active is red. You'll notice that some of the trails here are in dotted lines. The reason for that is that those objects crashed into and were absorbed by another object, and physics for that actually works. We put those in that disabled list I mentioned just a second ago, and they are treated differently therein by the program. That lets us choose how to display things that were destroyed. You can add an arbitrary level of detail to this simulation. As you can see, for the amount of time it ran, quite a few events happened. The beauty of the in-body simulation and how it operates with Matplotlib, or how it can be implemented, is you get these really graceful paths traced along through space. We've set arbitrary strengths for the value of gravity, so things here are actually behaving in a very extreme manner compared to how they would in real life. Because again, the difference in that g constant we saw a second ago. We'll take a look at this real quick. A quick note on this Matplotlib interface. With left click you can drag it around, with right click you can zoom in or you can zoom out. You can go back to the default level by clicking the home button, and you can change the parameters of appearance here, but this will also generally change your unit scaling, or how your axes are scaled. And of course you can save the file here as a PNG, which is what I will be doing here as figure 1. Back to the program, we have our function here that clears our lists. It chooses which objects are bold lines and which ones are dotted lines, based upon whether that object is dot active. Well, what object is that? Down here we've declared a class called body. here in line 29. We have our init declaration here. We have an xy value, a v value, and a mass. Xy is just its starting position. V is its starting velocity. And then we've assigned both of those to NumPy arrays. The mass is declared just as itself, and we have another value here, which is the object's radius. This is what allows two objects to crash into each other and one of them to be deleted, as we have seen in this example. The points at which these objects cease to exist are determined by the radii of two objects. When their positions and their radii overlap, one of them will cease to be. Whether or not something exists is determined by this value here, self.active equals true. And then, crucially for Matplotlib, we have a xlog and a ylog, which begin just as empty lists. This block highlighted here is responsible for all particle interactions during the simulation. It begins, you have to declare whether or not the object is active. If it is not, this will not run. This is a backup failsafe just in case your list methods above don't take, but it worked and this was redundant, but redundant safety features are generally an okay thing when you're dealing with operations that could crash your computer. Now we're going to go through all of the objects, in this case all of the bodies, in our active list that we declared in line 15. So each object will go through that list and check if the object it is looking at is also active. If it is active, it double checks to make sure that the object is not itself. This little part here is crucial because if this is not there, your program will end early. We're going to find the difference between the two objects' positions, and then we're going to find the distance by utilizing a NumPy function, in this case numpy.hypotenuse. We're going to declare the two arguments there as the dist here, x and y. If that r value is greater than the 2 radii times your dt value, then it will run as normal. Why are we multiplying it by dt? Well, because dt is the measure of our accuracy. How can you be sure if two things hit each other? Well, you can't when you're trying to predict the future. So what you do is acknowledge the sheer level of inaccuracy you are working with and just incorporate that. It keeps things a little bit more elegant. It also keeps you from breaking the laws of physics quite as much as you otherwise would. As per the standard Newtonian gravitational equation, we are going to be multiplying big G by our delta T value, and then multiplying that by the object's itself mass and the beta object's mass. That gives you a value called mu, which you then divide by r squared to get the force, and then you multiply that by your difference in position over the distance between the two positions, in a value called r hat for mathematicians. You multiply that all together. You account for inertia by dividing this Fg value by the mass, and that gives you a change in velocity. This loop will go through every single object that is active and acquire a change in velocity based upon that, and store it in that object's v value. However, if those two objects are too close together, we need a separate function to remove them from the loop. in which case we need to find the combined mass of the two objects, the average position of the two objects, which is just one xy plus the other xy, and you divide the both by 2. In this case, we're doing integer division just to save, I don't know why. We don't actually have to do that. Don't worry about it, we'll get rid of that. Then we have our combined velocity, which follows Newton's laws. We have to multiply our mass by our velocity and the other mass by its velocity all together and divide that by the combined mass. Why is this an integer division? Well, because whenever I was running it before, it tended to require a much greater amount of floating space. Anyway, we're also going to declare that the secondary beta object is no longer active and that the self object's new mass is the combined mass, its new position is the combined position, and the new velocity is the combined velocity. We're also going to recalculate this radius value, which is just derived from the volume of a sphere. If this occurs, we're also going to print in our progress bar, which I'll be covering below. It's not really a bar. We're going to be printing in the console just the phrase strike to inform us that one or more objects has been removed. We're also going to have a secondary function here, which we're calling translate self. If self is active, we're going to add the velocity times dt to our position, and then append our x position to x log and our y position to y log. That is so that the plot can interpret those values and utilize them later on. This for I in range 025 is how we randomly derive those objects and their positions. It's not too terribly important, but if you were interested, we're going to declare random x and y values from -5,000 to 5,000, and then multiply those by our kilometer constant. That means that everything takes place in a 10,000 kilometers squared area, I believe, according to the scale. Not that it super matters here. We've destroyed the scale by making g multiple orders of magnitude too powerful. We're also going to mark the object's starting position, and this is the first time you see this plot function being used. So all we're going to be doing is marking the random x value that we defined here and the random y value that we defined here, and we're going to be giving that mark a blue dot. So the letter stands for the first letter of the color you want to use, and then there's a secondary parameter in the string that determines the shape of the marker, in this case a dot. Now that we have everything defined nice and relatively pretty, we have to go through and actually make this data work. So while our elapsed time is less than our time limit, and while our active list has at least 2 things in it, so that there's a point in using it, we're going to be adding dt to elapsed time. That's because that's exactly what dt is. dt is the change in time, so every time you tick it forward, you have to add dt to elapsed time. We've got a secondary thing here, and this will count as our progress bar. So for every minute of elapsed time, or 60 seconds, as declined by the modulo operator here, this just says if we divide the thing by 60 and there is no remainder, we're going to acquire this value, which is our progress, which is really just our elapsed time divided by our time limit times 100, integer divided, so that we get clean numbers and not constant thirds, or repeating floating numbers. And then we're just going to print that value. That'll tell us what our percentage is towards completion. One thing to note is that for every object that is removed from the active list and added to the disabled list, the simulation runs a little bit faster. We're going to be utilizing at this point our call list function to make sure that it happens before anything else. This just reduces the amount of objects in active list before we run the process. So we're going to be running 2 loops through the active list. The first one goes through and calculates the change in velocity for all of those objects. Once we have calculated the change in velocity, then we are going to move all of those objects at once. You could, if you so chose, do these things both at the same time, but it would be important to note that some objects would be attracted, and then the object they were attracted to would move, and then other objects would be attracted to the new position. It just adds a new layer of uncertainty to your simulation. It's a bad practice. It's probably mathematically incorrect for multiple reasons. But that's going to run through the active list and run this loop over and over again until our progress equals 100. That is to say, our elapsed time equals our time limit. After that happens, we are going to go through everything in the active list and declare that x is all the values in each object's x log, and y is all the values in each object's y log. And then we are going to plot those as a simple line. This means that the color for that particular path is going to be random, but that is okay, it doesn't matter. And then we're also going to be marking active objects' final positions. That is the current position it has when the simulation ends. And then we will be declaring that object as a red orb or a red circle, and marking its position as a red dot on the plot. Now for objects in the disabled list, we will be doing exactly the same thing, but we will be declaring its ls or line style is equal to quote double dash, and that is how you get dead objects to equal dotted lines. We're going to declare the plot's axes to equal each other, so circles are circles and not ellipses. And then we are going to tell it to plot.show, and you are done. Whenever this thing actually begins, it just does this. As you can see, it'll pop up down here. It'll initialize, and this is running slow because I have OBS in the background. Hopefully that's why. There we go. It is just going to take it a hot minute. This is a very old laptop. It does not like me over much, and in fact, I am not going to make you sit here and watch this. Future me will likely edit this out. Anyway, I hope you enjoyed this video. Please like and subscribe. If you have any questions, comments, or suggestions, please leave them down below. I will get back to them as soon as I can. And if you have ideas for future videos, let me know those as well.